All right, let's continue our course review. In this section, we'll take a look at questions 5, 6, and 7 from the handout. That is applications, looking at curve sketching, optimization, and related rates. Question number 5 asks us to sketch this rational function. A quiz or a test or an exam question would probably have more detail about which features we're expected to label, but I suppose if we're given these directions, we should probably label all the features that we're capable of labeling. So I'm going to suggest that you start with advanced functions instead of with calculus here, and let's just analyze what we have. We are going to have a horizontal asymptote of y equals 0. I don't need to take limit as x grows without bound to determine that. I can see I am in a division form. I can analyze what happens as x grows without bound in my numerator and denominator. I'm going to have an x-intercept of 3. That is the one and only x-intercept that I have, and I will experience a sign change as I cross there. We'll have a vertical asymptote of x equals 0. That's the equation of the vertical line. With an even exponent, I will not change sign as I cross that vertical asymptote. So crossing the x-axis at 3 is the only time our function will change sign. I guess this means that we don't have a y-intercept. I feel like that's a decent amount of information. I wonder if I could actually even draw a sketch from here. I might need to do a bit of sign analysis and say, well, in the long run, that's positive and that's positive. So when x is greater than 3, my function will be, my function's outputs will be positive. So for that reason, I feel comfortable drawing a curve that is in the first quadrant in the long run. And that means that when I change sign by crossing that root, I'll be in the second quadrant. This is me approaching the vertical asymptote, and then since I don't change sign as I cross that asymptote, I'll draw my curve like that. I'm comfortable here not crossing the horizontal asymptote in this direction, since I know I don't have any other x-intercepts. I have a feeling that my calculus will verify this for me. It'll tell me that there are no critical points to the left here. I am expecting a turning point somewhere larger than 3 and an inflection point somewhere larger than that turning point even. Okay. All right, let's go to the calculus to find those values. We've got a quotient rule to do here. This is a quotient of two variable functions, so it seems like an appropriate use of the quotient rule. It's not, it doesn't have a constant denominator or a constant numerator, which I feel are inappropriate uses of the quotient rule. Let's do a derivative of the top times the bottom minus, how about derivative of the bottom times the top, all over the bottom squared. And I'm not sure this is a great time to factor. I don't think we should always factor or we should always expand. I think I'm going to choose to expand here just because expanding is easy enough to do. That'll give me a minus 2x squared, plus a 6x all over x to the exponent 4. Let's do f prime of x equals negative 1x squared plus 6x all over x to the exponent 4. How about I remove a factor of negative x minus 6 all over x to the exponent 4, and then I can simplify this other rational function like so. Okay. Oops. Like so. There we go. Now let's review that critical numbers can occur when the derivative doesn't exist, but it would have to be on a value that is in the domain of the original. So I think I'm just going to communicate for review's sake that f prime of 0 does not exist, but 0 is not an element of the domain of f. So there's no critical point when x is 0. I know that there's no point when x equals 0. So what was the point? I see a root when x equals 6, and that tells me that there is another critical number there. I see a root when x equals 6, and that tells me that there's a stationary point when x equals 6, but I also see a sign change. I don't need to find a sign change to find a critical number, but it was useful to check that definition of an inflection point. Seeing a sign change when x equals 6 tells me that there is a turning point at when x equals 6. I kind of was expecting that already based on my understanding of what this curve would have to look like from my sketch. So let's just communicate here. I see that there is a root when x equals 6. f of 6 is going to be 6 minus 3 all over 6 squared. What's that? 3/36 or 1/12. So this is 6 comma 1/12. And I'm not going to worry about making that height very small there. Is 1/12 a small number? There's a lot of numbers smaller than it. On to the second derivative, but from where? I guess we could do constant multiple with this negative there. I definitely don't want to use a product rule. Let's try constant multiple. I think I usually go from like a simplified version from here and a standard form in the numerator and denominator. We'll see how this works for me. Second derivative, f double prime of x, constant multiple of -1, and then another quotient rule. Derivative of the top times the bottom, minus, let's do the derivative of the bottom, multiplied by the top, all over the bottom squared. Okay, let's tidy this up. The common factoring is becoming a little bit more tempting here. Even division on this step is tempting, but can cause a lot of problems. I'm just going to expand. I avoid expansion when it is tedious, or I can tell that it's going to be more difficult. I am, I think, temporarily making my expression more complicated before simplifying it, but I'm comfortable with the level of expansion that I'm causing. Let's see, collect here to -2x cubed plus 18x squared all over x to the exponent 6. Remove a common factor of -2x squared. So that leaves me with x minus 9 all over x to the exponent 6, which will simplify to -2 x minus 9 all over x to the exponent 4. And if I want to do a sign analysis here, x to the exponent 4 is never negative. It is unsigned when x equals 0. It's neutral when x equals 0. So I shouldn't discuss concavity of f when x equals 0, since f doesn't exist. If I were to do a factor interval chart, I know that x minus 9 will eventually become positive, and -2 is always negative. So I believe that my concavity is going to be, since my second derivative is going to be negative and then neutral and then, negative, non-existent, and then neutral and then positive. I think we're going from being concave down to concave up, and that's what I see on my sketch. And I might have been cheating a bit there by looking at my sketch instead of actually doing a sign analysis in my head here. Our curve is concave down, undefined, concave down, and then concave up. One issue we did have on our sketches was that where students were putting an inflection point wasn't where your curve was inflecting. And I'm going to take some of the responsibility for that, because I would say humorous things, I think, like this is 1/12 because I say so. I take a lot of liberty there. I'm allowed to say that's a height of 1/12 because I've labeled it 1/12. But what I'm not allowed to do is look at this and say, here's an inflection point because I say so. No, it's not. I mean, I'm allowed to say that, but I'm also allowed to be wrong. I would say that that is where our inflection point occurs here. Okay, so try your best to draw a smooth curve and then label where your inflection points are. Do not put in a linear scale and at 3 put a root, and then at 6 put a turning point, and then at 9 put an inflection point. That kind of looks like what I've done, but if you watch the video again, you'll notice that I just drew a smooth curve and identified where these turning points and where these inflection points occurred. Is that, you know what, I'm going to make that big enough so that it'll be harder to argue that that's the inflection point. Okay, definition of an inflection point is where the second derivative changes sign. Review, g of x equals x cubed. Actually, that's not a great example, but worth reviewing as well. H of x equals x to the exponent 4, and j of x equals the cubed root of x. These two are the more interesting examples. This function, its second derivative has a root, but you know that a parent quartic does not have any inflection points. This function, I think from your familiarity with the inverse of a parent cubic, you're expecting it to have an inflection point, but its second derivative doesn't have a root. So second derivative has a root, no inflection point. Second derivative doesn't have a root, does have an inflection point. And that's because you are not looking for roots when you are looking for inflection points. Okay? You are looking for a change of sign. And that was the communication that I was looking for anytime you were asked to find an inflection point. Not that there's a root here, not that you set f double prime of x equal to 0, because that's not what you're trying to do. You are trying to figure out when this expression can change sign. There is a sign change when x equals 9. Technically, you might want to actually say like over x equals 9, because it's across that value that the sign change occurs. Fine. And that is why we know there is going to be an inflection point at 9 comma f of 9. F of 9 is going to be 9 minus 3 all over 9 squared. That's going to be 6/81, which is 2/27. Yeah. And so I will label this inflection point, which I have labeled where my curve inflects, 9 comma 2/27. Maybe I'll identify that as being a turning point and this right here as being an inflection point. And I've labeled my curve, so I'm about set. Other things that we should have been able to do here include finding a local maximum and minimum over an interval, or an absolute maximum and minimum even over the entire domain. I suppose we should be able to use limits to analyze the end behavior. We should be able to give intervals of increase and decrease and intervals of concavity as well. Okay. It feels like we just did this stuff. I guess since we might have used this question as review since after the closure. Okay, question 6 is one of those cable problems. Let's just make sure I can see the whole thing. You want to run a cable across a 200-meter wide river. So I'm starting with a sketch and hoping that I have enough room on my page for this. And 2,000 meters downstream, not to scale. But it costs $8 per meter to run cable underground and 10 meters to run the cable underwater. How should you plan to minimize costs? Declare your variables. Let's let C of something represent the cost in dollars. Get your dependent variable out of the way. As the idea here is we want to choose one simple independent variable. Here is how I'm visualizing running my cable. I think I should probably run it underwater, not directly across, because that would maximize the distance that I'm running it. The sort of extremes over the interval here are that it wouldn't make sense to run it backwards. So the distance that I'm running above ground should be between 0 and 2,000 meters. It also, I don't think, would make much sense to aim for a point past here and then run backwards. Sometimes the mathematics will return an answer if it thinks that running backwards is a negative cost. And then you've found a way to make an infinite amount of profit by just running cable backwards for the rest of your life. Yeah, so here's my idea. Now, I mean, it could turn out that maybe running it underwater the entire time is the best option. And however I set up my independent variable, maybe it'll tell me to what this angle is. Maybe it'll tell me what that distance is or what this distance is. That distance there could be 2,000, or this distance here could be 0 in that case. The angle, I guess, would be the inverse tangent of some ratio between these. I don't think that setting this up, sorry, I mentioned the angles. I don't think setting it up as a trig function is really the best bet here. Unlike the putting a ladder around a corridor, where getting one expression in terms of one unknown was kind of challenging. We had a couple of different unknowns there. Here, I'm pretty sure that I could define this in terms of the length underwater or the length above ground. Those wouldn't be the easiest choices. I think we found that using this distance right here, I don't know, maybe I'll just call it D for some sort of distance. It's actually the distance that I'm not running above ground. Turned out to simplify that expression and simplify that expression a little bit. Okay. Let's let D represent, and I could say the distance to not run it, but I feel like it might be better to explain that this is the distance downstream at which I want to aim. The distance downstream. Is it downstream or upstream? Doesn't matter. I don't know. At which to aim in meters. And I think I will communicate these distances in a sentence as well, just to clarify things for my reader. Notice the relative ease with which we can find expressions for that distance and that distance. If you used this as your independent variable, this is a mess. If you use this as your independent variable, this is a little bit messier. It's not that bad. I saw a couple of solutions like that. I'm going to say then the distance on land is 2000 minus d, and the distance underwater is the square root of d squared plus 200 squared. Okay, and that might just help me, especially if I'm starting in English here and I say that the total cost is going to be the $8 underground multiplied by the distance underground, plus $10 per meter multiplied by the distance run underwater. Now I can just substitute in my function that this is going to be 8 multiplied by 2000 minus d, plus 10 multiplied by the square root of d squared plus 200 squared. Okay. We have set up the cost to be a function of a single independent variable. We can now optimize this cost, hopefully find a minimum. We could run an extreme over an interval algorithm if we weren't convinced that it's a minimum. I have a feeling if we find a value of d between 0 and 2000, that we could probably conclude that it results in a minimum without the need of it for a test here. I'm going to choose not to expand and not to complicate that thing. I think I'm just going to differentiate in this format. Expanding here isn't really going to do much for me in terms of simplifying my derivative. So c prime of d is going to be constant multiple of 8, derivative of 2000 is 0, derivative of negative 1d is negative 1, plus 10 times the derivative of the outside here, 1/2 of d squared plus 200 squared to the exponent negative 1/2 multiplied by the derivative of the inside, 2d. Derivative of 200 squared. You could do 2 times 200 times the derivative of 200 with respect to d, but the derivative of 200 with respect to d is 0, and I kind of feel like that demonstrates, it doesn't demonstrate an understanding of the chain rule. I think it demonstrates a misunderstanding of the constant rule. Our goal here is to set c prime of d equal to 0. While I do that, I think I'm going to tidy up this function a bit. That'll be negative 8. Let's see, 10 times 1. Well, I was going to do 10 times 1/2, and I decided instead to do 1/2 times 2. So I'll be left with a factor of 10 and d in my numerator. In my denominator, I'm going to have the square root of d squared plus 200 squared. Okay. I'm going to add 8 to both sides and multiply both sides by this square root. So that's going to be 8 multiplied by the square root of d squared plus 200 squared equaling 10d. Maybe I should simplify those coefficients. I think I'm going to sneak that in on this step so that I just don't have to show another step. Okay. And then solving for d here, one instance of d is buried underneath that radical sign. So let's use the strategy of squaring both sides. Just make sure you understand how equilibrium works and you understand that you have to square the entirety of both sides. You are squaring the left side and squaring the right side. 4 squared multiplied by square root of d squared plus 200 squared is d squared plus 200 squared. I'm really avoiding doing 200 squared for as long as possible. I don't know if it's going to pay off. Equals 25d squared. Sorry about the space. I guess I'll just distribute that 16 d squared. Now I suppose is the time. Let's just see. 16 times 200 squared. It's a big number. 25d squared. How about we do 25d squared minus 16d squared and do 640,000 divided by that number. And then take its square root, maybe all in one step, and we get d is about 266.7. We dismissed any negative value. Again, it's an interesting conversation to see why it reports a negative value. It does think about a negative cost here, or you could argue it's just the quadratic thinking that there's a second solution. So aim about 266.7 meters downstream to minimize cost. The question, the conclusion that you're looking for is also a little bit open. I suppose you could say how much you need to run underwater and how much you need to run underground, but the question didn't ask for that information. So you can give, now would be a decent time to find the angle as well, but I guess if you wanted to practice trig derivatives, you could set this up as a function of either this angle here or this angle here, but you're making the question a little bit harder than it has to be, I think. Go ahead. And question 7. Question 7 says the foot of a 10-meter ladder slides away from a wall at 0.5 meters per second. So here's a 10-meter ladder. That ladder is not changing length. The length of the ladder is a constant. dl by dt is 0, but how about I just treat it as a constant instead? The bottom of the ladder, the foot of the ladder, yeah, slides away at 0.5 meters per second. I'll probably switch that to 1/2. How quickly is the height of the top falling when the foot is 6 meters away from the wall? Notice I am not labeling 6 meters on here because it is the instant. I'm going to communicate when in my solution I use that instant value, though, clearly. Let's see, I'm going to call this H. I'm going to call this maybe B for base. Let's say we are given delta B by delta T is positive 1/2 meters per second. We are asked to find dH delta H by delta T when the top is 6 meters away. H equals 6 meters. Okay, again, I'm communicating that that's part of the instance, but I'm going to hold on to that value. My favorite approach here is to start by, well, sorry, my favorite approach is to declare variables. I love declaring variables. Let's let B, H, and T represent distance from the base of the ladder to the wall, height of the top of the ladder, and time. Notice we weren't given any information about time or time's reference here, but we do need to declare it because we are differentiating with respect to time. But I don't know if this is time since observation or time since whenever. It's really, you decide, but it's not information that's given in the question. So I don't think it should be defined on your page. We will need units in meters, and seconds. If this were asking us for the rate of change of the angle with respect to time to make sure that our units would work out, we would need the angle to be measured in a unitless ratio. That would have to be done in radian mode. This one is not talking about the angle. So, Okay, my favorite approach is to relate the variables first and then differentiate with respect to time implicitly and find a relationship in the rates. I don't think that building the chain first really worked well for most students here. I had a couple of students try it, and it usually didn't result in fantastic things happening. So the relationship between these variables is that h squared plus b squared is always going to equal 10 squared. Okay. Now, since I'm trying to use dB by dt and I'm trying to find dH by dt, I am going to differentiate with respect to time on both sides. I do not need to isolate h for that to happen because I know how to differentiate implicitly. Right? Couple of chains here. Derivative of a sum is the sum of derivatives. The derivative of h squared with respect to t is going to be, I'll show the chain, the derivative of h squared with respect to something multiplied by the derivative of something with respect to t. How am I going to chain from h squared to t? About through h. I could use any variable that I want, but this will be delta b squared delta b times delta b delta t. And over here, you could do the derivative of 10 squared with respect to 10 times the derivative of 10 with respect to time. If you don't understand that 10 squared is a constant and the derivative of a constant is 0. Let's simplify things. Okay, I wasn't impressed by sort of a dependence on derivative rules instead of a demonstration of an understanding of derivatives that shows. Okay, if you don't want to show this step at all, I think most of you were fine writing 2h plus 2b, 2h dh by dt plus 2b d delta b by delta t equals 0. Let's divide both sides by 2. I suppose now we could try to isolate for dh by dt. Or we could sub all knowns. Or no, let's take, you know what, I'm just going to simplify it. H dH by dt plus B delta B by delta t equals 0. So now we take inventory. We say this is what we want. This was given. This was given in the instance, so this is what we need. So now, below this line, to the left or below, like following in the order of my work, this is where I'm going to show that I can calculate what B is when H is 6. And this is where I'm going to communicate that I'm substituting in all of my notes. Okay, H is not 6 in this question. That's related to the instant at which I'm trying to find these related rates. And I think a couple of us, the biggest problem here, I think, was just realizing that we're responsible for the organization of our solution. That you're still not just trying to get an answer, you're trying to present a solution in a way that a reader can follow. I mean, take the Grapes of Wrath and randomize the pages, and it is not a great work of art anymore. I don't know, is Grapes of Wrath a book? I heard someone talk about it before. Let's see. So when h equals 6, now is also maybe a decent time to draw a sketch. 6, 10. Maybe I recognize that this is a Pythagorean triplet, but I am trying to present a solution. So I'll say b is going to be only the positive root of the difference of these squares. It's 3, 4, 5, yeah, 8. Right. B is equal to 8. Let's sub all knowns. And I get that 6 times d to h delta t plus 8 multiplied by 1/2 is going to equal 0. Let's see here. 4, negative 4, negative 4 sixths, negative 2/3. 4, negative 4, negative 4 6. I think so. Yeah. And I'm not surprised that delta h by delta t is negative. I was expecting this ladder's height to be decreasing as time increases. It's usually easier to forget to interpret the sign when you end up with a positive rate. Think about interpreting the sign of all rates when you come to your conclusion. Let's say at that instant, the top of the ladder is falling at a speed of 2/3 of a meter per second. Okay, we will wrap things up with questions 8, 9, and 10 in the next video.